So welcome everyone to the NPTEL Introduction to Mobile Robotics course TA session. Uh, I am Suraj Borate, PMRF PhD scholar from IIT Gandhinagar, and I will be conducting this TA session where we will be solving previous year's assignment 7 question, and the questions that we will solve will be very similar to the this year's assignment 7, and will hopefully help you go like solve all the questions in the assignment very easily. So let's move on to the first question. So a robot is not only a mechanical architecture but is also slaved by the impacts its performance. It's slaved by that impacts its performance. So what is that thing which is like the boss of the robot, right? So that is the question. So can anyone answer this? Very simple. So this is like the first lecture of this week where this sir might have discussed. So the answer is controller. Okay. So what happens is so let's see. So sensor is something that gives us information, okay, about the robot or surrounding or environment, right? So it can be the state of the robot or the where the obstacles are present and all. What does a planner do? Planner will plan a path or an action for the robot depending on its task or the objective, right? So something like a collision-free path from point A to point B. Okay. Actuator, what is an actuator? So actuator is actually that limb or that body part of the robot which actually moves, which are actually causing the motion. Okay, so it is something that will apply forces on the environment and cause the robot to move. Okay, so that is the actuator. So it can be a motor or a linear actuator or something like that. A navigator may be something like a map or a SLAM algorithm, which is like building the map, telling the robot where it is, localization algorithm, which takes the sensor inputs, takes the robot model, the robot dynamic equation or the kinematic equation, and then tells about directions and the positions of the robot. Okay, supporter, I don't think there is something called a supporter. So but the controller is actually the thing that is the boss of everything, because the controller will take inputs from sensor, and the navigator take the desired input from the planner, right, and output the control command, and this control command goes to the actuator. So this is essentially the brain, right? So here you have the eyes and all, and this is the controller. Okay. Okay, so it's the controller. In actual robot, you will have this everything on a microprocessor or a controller. Okay, the code will be here. So this is a very basic question. So let's move on to the next question. Seamless integration of inaccurate models and limited sensing capabilities is known as. So seamless integration of inaccurate models and limited sensing capabilities. So what happens is whatever mathematical model is derived using the first principles usually have lot of assumptions. Okay, a lot of assumptions are there. Okay, and these assumptions do not are that we are not going to include each and every effect that the environment might have on the robot, or the each and every aspect of all the forces or its of robot's motion are not considered. Only the dominant aspects are taken. Okay, and we derive the model. So for example, if there is a If there is a car, then we have a simple model for that, like dynamics model we have derived car for a car like robot. So we didn't consider that okay, that particular tire might be deformable or something like that. We developed it for hard tire. Okay, so we didn't consider okay, what is the friction coefficient or something like that, or how the friction coefficient might change, or what is the friction between the bearings where the wheel is mounted, and so we don't go, or the suspension or something like that. So always we have the simplified model which is inaccurate, and all models are inaccurate. Okay, and limited sensing capabilities. Even if you have sensor there, it will have some variance. Okay, or you may have less number of sensors than required. So when so many uncertainties are present in a robot, then we need something to you know to derive the best possible estimate or the best possible information from all this uncertain data that we have, and that is done using the field of probabilistic robotics, because now you have something like probability only, right? So you don't have the exact information, so you are unsure or uncertain. So you are like, okay, there is 70% chance that robot might be here. Okay, might be here. So it is, so we have to play with something called as probabilistic robotics. Okay, soft robotics and other things are okay. So for example, what is soft robotics? Soft robotics is a field of robotics where you know the robot itself is soft, literally soft. So it can deform, or so for example, there are grippers like this, okay, which can be actuated by inflow and outflow of air using valves over here, and some compressor. Okay, compressor. So you can actually inflate and deflate this gripper. The finger can close and open. Okay, so such robots are called soft robots, and this is made up of some soft material. Okay, so it can have different types of actuation techniques and all. Field robotics is a field where we talk about building robots for different environments like underwater, um, off-road, or something like that, space robots. So that is about field robotics. Hybrid robotics is again combination of different type of robots. Okay, so those things are there. Uh, Sorry for the disturbance. Okay, so let's move on to next question. The inverse differential kinematics or inverse dynamics is equal to, so inverse differential. So just let's try to recall what is IDK, inverse differential kinematics. So it was what? Eta dot is equal to, okay, someone is joining. Let me just check who is joining. Okay, okay. So what was the equation for inverse differential kinematics? Who will tell? You remember or you have forgotten? So this was the equation. So what was eta? Eta was x, y, and theta, right? And zeta was what? U and v. So what was u and v? U was the body frame longitudinal velocity, right? And v was the lateral velocity of the robot, right? So what is this? This is what forward differential kinematics. So inverse differential kinematics was the dot zeta. Okay. So getting, and how the zeta was related to the wheel input, it was related like this, right? So this was what? Wheel configuration matrix, and this was the actual wheel angular velocities. So So inverse kinematics or inverse dynamics is equal to the feed forward or open loop control, right? Okay, so let me explain the terms feed forward and open loop. Okay, for those who haven't any have any background about control. So okay, so what is the meaning of feed forward? So let me just add one slide over here so that we can have space to write slide. Okay, so let's say you're driving a car. Okay, you're driving a car. Okay, and now you know you are seeing around, like when you press your accelerator, your car moves forward. Okay, and then whether to move left or right, you balance the steering. If suppose you want to move straight but the car is drifting towards left, what you will do, you will slightly turn the steering around and you will try to balance, right, the car to be on the lane. Now let's say uh, if we put if you blindfold you, if you put some cloth on your eyes and we blindfold you, then you will not be able to see. So in that case, how you will make sure that your car will move straight only? Okay, or if you want to reach a destination and you remember entirely, like, okay, I will press the accelerator for 10 seconds, then I will take steering, then I will do this and all. Okay, so you try to memorize the choreographed driving commands and you do, whether you will reach the destination if your eyes are closed. Anyone? You have remembered all the commands, when to press accelerator, when to turn the steering, everything, and for how much time, whether you will reach your destination. Am I audible?
Yes, sir.
Yeah, so you won't reach the destination, right? You will go and hit somewhere because your eyes are closed.
Yes,
Yeah, so
yes, sir.
why is that happening? That is happening because there are some disturbances. So even if you remember all the commands you have to do, when to turn steering and all, if you close your eyes, you will hit something. Why? Because there are disturbances. There will be some small pothole, or the car will not behave exactly every time the way it is supposed to behave. Okay. So why that is happening is because there is no feedback. Okay. So your eyes, when they look at the environment, they understand that okay, your car is not moving straight, right? So it gives a feedback to your brain. Okay, see, the car is not moving straight. The brain tells the hands that okay, you have to rotate the steering. Okay, but suppose that that feedback is not present and your eyes are closed, and just based on the calculations and the equation of the car, you do the commands. Then that is called open loop control. Okay, because there is okay, I will draw the control block diagram. Then you will understand. So this is the controller. Okay, someone is joining. Okay, Praveen only reconnected. Okay, so this is your eyes. Okay, this is your desired location where you want to go. Okay, your eyes will tell you your actual location where you are or in which direction you are moving. Okay, so here is the error in the desired location and the actual location. And this is the controller, is nothing but brain, which tells okay, this is the steering command you have to give to your hands, let's say. Okay, so what happens is, so this particular thing is closed box, right? It's a closed box, so it's called closed loop control. Okay, so this is called closed loop control. Now suppose that your eyes are closed, your eyes are closed. So this particular thing is cancelled, right? Then what will happen? There is only you know your desired location, and that goes to the brain. Now brain does not have like no connection with eyes. Eyes are closed, so it will just directly give steering command through its memory or calculations. Okay, so this is called what? This is called open loop control because the loop is not closed. Okay, so under disturbances, this will not work. If everything is perfectly calculated and there is no disturbance, every system is, if entire thing is perfect, all equations are correct. In ideal situation, this will work. Okay, so this is called open loop control or the feed forward. So this is called a feed forward path. See, the signal moves forward. So this is called feed forward path. Okay, so that is why it is called feed forward control. This particular control is called feed forward. Okay, and because here feedback path is there, closed loop control is also called
దానికి
feedback
లేట్
control.
అయింది. నెట్వర్క్ అయిపోయింది అమ్మని బాగా బయలుదేరి వచ్చింది.
So any question or the mic is
కానీ అంత బాగానే ముందే ఇది వచ్చింది.
అయ్యో వీళ్ళది కొంచెం ఆపి అది
okay? Praveen, you can mute. Okay. Yeah. So you understood the difference between open loop and closed loop control and feedback and feed forward control, right?
Yes, sir. Yes, sir.
Okay. So let's. So now you see here that inverse differential kinematics is equal to the feed forward or open loop control because that equation is there and we are what we are doing, we are finding what should be the input and we are giving. So there is no sensor based thing going on over here. So it is open loop control. Okay. So robust control aims at controlling with a small error a class of robot manipulators. Model is not accurately known with the same controller. Okay, so let's understand the meaning of robust control. So we understood what is control over here, right? So what was control? Control was we had something what is desired variable, okay, and then we measured something and we got the actual what is the value of that thing. We found the error and then we gave to the brain of the robot, okay, this is the error. You figure out what action should be taken. Okay, let me just change the color of the marker. Okay, so this particular brain it shows what action should be taken based on what error. Okay, and that action can be steering of the robot or increasing or decreasing the speed of the robot, whatever. Okay, and so that is what is called controller. So control output is some action, control input is the error. Okay, so the input to the controller is the error and the output is some action. Okay, so now here it is saying the word robust control. So what does robust control mean? So suppose for this particular system, the car, okay, there is also some disturbance that is coming in. Okay, so there is some disturbance. Let's say you are driving in a highly mountainous area on let's say Leh Ladakh, and a lot of wind is coming. Okay, wind is blowing, and so in that particular situation, you have to drive. So what will happen is whatever this controller logic will be there that you are using to drive in a city like Mumbai and all. Okay, let's say it was some kp into error plus kd into error dot. Okay, so this was the logic. Okay, so what it is saying, you move in the direction opposite to the error, right? So it's saying that okay, if suppose the error is high, then you move fast. If the error is low, then you move slow. and if the error is negative, you move in the ulta direction. If the error is positive, you move in the straight direction. So for example, let's say that okay, this is the path that the robot has to follow, okay, and the robot is, let's say, here, okay. So let's say this is the error, x error, okay. Let's focus on only one error, okay. So what does kp into e means that, so desired was 0, okay, your robot is, let's say, at -1, okay. So what it will say, so -1 minus 0, sorry, 0 minus -1 will be the error, okay. So because it is x desired minus x, so desired was 0, okay. So and kp value is 2, okay. So what it will be, what will be the control input, it will be positive 2. So the robot will move in this direction. Now suppose the robot is here. Now what happens to the error? Error is positive 1. Sorry, now the position is 1. So what happens? So desired position is 0 minus 1 into kp. So if kp is 2, then it will be -1, so it will be -2. So now the force or the action will be in the negative direction. So that is the thing. So if on the opposite side of the desired input you are getting opposite direction control input, okay. So our desired output, if you are more than desired output, you will be pulled towards the desired output. If you are less than, still it will be pulled towards the desired output. So that is nothing but proportional control, okay. And if you are very far, let's say very far, the error is more, so it will be 2 into 0 minus, let's say, -10, right. So it will be 20. So more further you are, you will be pulled that much fast, right. Okay. So for your particular application, you will choose the kp and kd, right. Now what happens is, there are some disturbances that is stopping the robot from, reaching the desired position. There's friction or some wind and all. Then in that case, you will require this kp to be even higher, right. Okay, so I'm giving you the intuition, right. So suppose that, okay, this was 20 was required to reach here, but there is some disturbances. So you need kp gains to be higher. Okay, so that is why we need, for robust control, okay, with a small error. So robust, the word robust means that even in presence of disturbances, in presence of disturbances, or or changes, okay, let me make some space, or changes in robot parameters. So when we say robot parameters, it can be the weight of the robot, okay, thus let's say some wear and tear in the robot, okay. So whatever so even when things change, the control should perform within certain bounds, okay. The performance of the control should remain within certain bound, or it should perform well. So that is called robust control, okay. So here we are saying that the model is not accurately known, right. So for example, we don't know the robot parameters or the equation itself, still it should work, okay, or in presence of disturbance with the same controller, okay. So it is not that we are changing the controller always. So if the situation change, then we'll change the control. No, with the same control logic, it should work, okay. Maybe you choose higher gains, but it should work. So that is called robust control. So it is true, okay. If it is, the question comes that instead of same, but okay, like changing controller or varying control, then it is called adaptive control, okay. Okay, so asymptotically stable means, what does asymptotically stable mean? So first of all, let's understand the meaning of stable from the control system perspective. So the word stable from control system perspective, actually there are different definitions of stability. Okay, but let me give you just the intuition. Okay, it's not a rigorous definition. Okay, so what does stable mean? So whenever we talk about some robot or some system, okay, we have certain, or a control system, let's say, we have a certain variable, okay, that we want to track, or set its value to certain constant or a varying signal. Okay, if suppose we are not able to set the value to certain desired value, because the value blows up to infinity, right? So something like, suppose you have a geyser in your bathroom, right? Geyser in your bathroom, okay, and it's whatever you set the temperature. Let's say you set temperature to 70 degree or 100 degree or something like that. Okay, then the water which comes out is like at 100 degree, suppose. Okay, so this is water heater. Now suppose what happens, that the control system is designed in an improper way. Okay, that will never happen, obviously. But suppose you are an engineer and you are working on a new geyser, and you choose the gain or the system parameters in such a way that the system becomes unstable. Then what will happen? The temperature of the fluid will keep on rising. Let's say it keeps increasing, keep increasing till something blows off in your system. Okay, so that is what is called as unstable. Unstable means that your variable which you want to control, okay, it will just increase in positive direction or negative direction or something like that, and it will not stabilize to certain value. Okay, so this is something called as, the most basic definition is bounded input, bounded output stability. So when you are giving a bounded input, obviously if you give infinite input, then the output can also be infinite. But if you are giving some bounded input which is not infinity, but still your system gives an output which is like infinite. Okay, so then the system is not stable, right? So for example, let's say that there is this block that is kept over on ice, and you apply some force F, okay, is equal to 1 Newton. What will happen to the position of the block and the velocity of the block? It will become infinity, right? Because the acceleration will, suppose this is 1 kg, acceleration will be 1 meter per second square. So because there is acceleration, velocity will keep on increasing, and position will also keep on increasing, because there is velocity, right? So this system is unstable because I gave only 1 Newton force, which is a bounded input, but I got unbounded output. Okay, so this is an unstable system. So now that we know what does stable mean, let's understand what is asymptotically stable. Okay, so we saw the example of unstable. Now let's see the example of stable system. Okay, so let's say that, okay, mm, there is this pendulum and it is here. Okay, so this particular point is a stable point, because whatever equilibrium point. Okay, so if you move this pendulum over here and we release it, it comes back to that point, right? It comes back here. Okay, so this is called stable equilibrium point. Okay, so whatever initial condition we leave the system, it is coming back, right? So that is nothing but stable. Okay. If you see the opposite case, okay. So let me draw it straight. Okay. So this is what theta equal to pi. If this is theta, then this is like theta equal to pi. So this particular equilibrium point is unstable equilibrium point. So if I leave it from here, then it will go down. It will not come back to this position, right? Okay. So stability can also be seen from the that perspective. Now, when we say asymptotically stable, it means that as the time tends to zero, the tracking error also tends to zero. So it is something like this, like e to the power minus x minus t. So as t tends to infinity, the tracking error should go to zero. So that is called asymptotic stability. There is another form of stability where uh, the error need not go to zero, but we are not going to discuss that over here. We want our system to be asymptotically stable or exponentially stable. Okay. In a set point or regulatory position control, the desired position vectors and velocity vectors are continuous. Okay. So um, this is. Can anyone answer this? Is it true or false? So what do you mean by set point? So set point means that there is only one constant value you want. So okay, let's say this is t equal to 0 and this is t equal to 10. So this is what you want the position to be. And this is the desired position, x desired. And let's say your current position is somewhere here. So what will happen? This will be the error, and then you have to your desired position will be what? Upward like this, right? So this is not a continuous function, right? Is this continuous? No, it is not, because there is a step over here. So that is the problem. Okay. So a set point is not a continuous control strategy. So this is false. Okay. Second order error dynamic is stable as per the following condition. Okay. So when we say dynamic is stable, we are again talking about asymptotically stable. So if you when you are saying asymptotically stable, the solution should look something like that. The error will be like this. Okay, e to the power minus t. So which differential equation yields an exponentially decreasing solution? So that you have to check, and I think it is this is the answer. Okay, so if you see this particular equation, so both the coefficients should be greater than 0. Only then you will get something like an exponential decreasing solution. Okay, so this you can actually verify by substituting inside. Okay, then the vector of input commands or control inputs of computed velocity control is given as. Okay, when we are saying velocity control, it means that we are using only the kinematic model, not the dynamic model. Okay, uh, and so what was our basic equation? It was zeta is equal to j inverse of pi into eta dot, right? Yeah. Hmm. And so we will have what? This was what our, this will be the inverse dynamics control or the feed forward term or the open loop term as we had seen earlier. Okay. And so how are we going to derive this? There should also be a closed loop term, and let me check the notes. Okay, okay. Okay, so this is for the desired, right? So this is feed forward is where we know the motion of the vehicle, and for that we are closing our eyes and deriving the control input just based on the equation. So here we put the desired, okay, and then for the feed forward okay, so this is the eta feed forward term, right? And for eta feedback, what do? We use the error. So what we will do, we will have j inverse of 5 uh, into the error with respect to time into some positive constant lambda. Okay, and then what we will do, we will have eta as the combination of eta ff plus eta feedback. Okay, so that is eta is equal to, if you take j inverse of phi can be replaced by eta, okay, and inside that we will have eta d dot t plus lambda into error. So when we say this is nothing but eta desired minus eta, okay, and so this is the answer. Okay, if you have any doubts, you can please ask. So we want both the feed forward and the feedback term. So I explained feed forward and feedback in this slide, right? So this is the feedback and this is feed forward, right? So here what we are saying, we will also add, so this is desired low, we will add some uh, j inverse of eta into uh, eta dot desired, and we'll add over here whatever will be the output of this feedback control, we'll add here, and then the output will go. So what we are saying, that at least suppose you want to turn on a switch and our eyes are closed, okay, then our hand will go towards the switch but not exactly, it will go nearby the switch. Let's say our eyes are open, okay, then our hand will go towards the switch very quickly, and when it is near the switch we will just, okay, look very carefully and then press the switch, okay. But on the way we don't do. Why? Because we have already, our mind knows that, okay, this direction we have to move, and there it not lot of feedback calculations are required. Only when to do the precise action we need. Okay, so the information of feed forward is utilized, and the correction is done, accurate corrections are done based on feedback. Okay, so we need both combination of feed forward and feedback. Although we could do based on only feedback, but then that is unnecessary, right? If you have the information, you should use, so that will save a lot of energy. Okay, otherwise the feedback will have to calculate everything, uh, and some it will try to compensate it. Sometimes it will overshoot. Okay, so those things won't happen. Okay, let's move on to the next question. The motion control is a subfield of encompassing the systems or subsystems involved in moving parts of machine in a controlled manner. Okay, so this is again a theory question. So what do you think is the answer? Okay, so let's not waste a lot of time. This is automation. So it's just saying that, okay, so when you want to automate something, you a moving thing or something like that, so you motion control will be a subfault. But I don't know, like navigation also can be the answer, because in navigation also you need to control motion, but it's fine. I think automation is more relevant over here. Okay, so what is the primary or important control objective? Obviously stability. If your system is not stable and going to infinity, then your system will blow up. Something will go wrong. Some actuator will go, or something will happen. Wrong things will happen. You'll lose your components. Okay, so stability is the prime thing. Only after that we can think about tracking performance and all. So when we say tracking performance, if suppose this is your desired output, it's about in how much time you will reach here. Let's say this time, okay, or how much overshoot will happen and then it will stabilize. So those things are comes under tracking performance. But to think about this, first our system should be stable. If your system is like this, going to infinity in no time, then there is no point, right? So first stability and then these other things. Okay. Okay. So that dash is the change of state at any instant in time of a body. Obviously motion. First motion. Dash is the state of a body or bodies over a period of time. I think this path. Okay. 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 Sorry. So this is trajectory, and dash is the position of body over a time without worrying about. Okay. Yeah. So the thing is, yeah, it's just wordplay. The thing idea is that, okay, first is very easy. Change of state is motion, but path and trajectory means that, okay, path means there is no temporal information, no time information. Okay, you travel some path. Now this path can be traveled in 5 days or 1 day or 1 minute. It doesn't matter. Path is a path. It is some curve of x and y or z coordinate. It's just a path. Okay. But trajectory, it means x of time, y of time, and z of time or theta of time. It is something where the time evolution of the path is given, where the velocity and acceleration and jerk and all the derivatives become important. Okay, so that is trajectory. So it's x of t. Once x of t is given, you can find x dot of t by derivating it, or y dot of t by derivating it, or x double dot of t by derivating twice, right? But path is a path, just a path. There is no time information, so you cannot find any velocity for a path. You have to choose a velocity for a path, right? So let's move on to the, okay, so all the questions for today are done. Uh, if you have any doubts or you want to ask something, please ask. Praveen, Aniket. So your exam timetable or something has come, I think so. So all the best for that. So we have one more week to go. So next week also same time I will be here. Um, I think next will be the last session. So come up with your doubts. Today also, if you have something left to ask, you ask. Any particular question you want me to repeat or anything else from the course or the slides? So I'll wait for 5 minutes for you to ask questions. And if you don't have any questions, then I will just end the session. No questions? Are you there, or you have just joined and gone to play or something like that? Okay, so I will assume that there are no questions, and I'm ending today's session over here. Thank you for joining, and those who will watch it on YouTube. If you have any doubts, you can put it in the comments. I will try to answer them, and see you next week. Bye bye.